Hello, everyone. In the last lesson, we've analyzed the measurement requirements for the CNC milling part according to the drawing and complete the establishment of the coordinate system. Next, we will cover manual measurements for the typical features of the machine demo part. After learning from measuring the demo part, you should be more familiar with the basic operations and measurement processes of the CMM. Before starting feature measurement, it's important to mentally go through the entire process and choose an efficient measurement sequence to achieve optimal results. Next, we will cover manual measurements for the typical features of the machine demo part. Through this hands-on session, I hope everyone will be able to accurately measure various features on the demo part, such as distances between planes, diameters, parallelism, etc., and ensure the accuracy of the results. After completing the measurements, you should be able to evaluate the dimensions of the demo part based on the results and judge whether they meet the drawing requirements. During the measurement process, due to factors like surface machining quality or setting issues with moving parameters, there may be occurrences like probe interference or slipping. It's important to identify and address these problems patiently during the measurement. Precision work requires patience and attention to detail. Precision measurement is a very strict precision requirements of the work. Therefore, we need to have the quality of meticulous work. By reviewing the measurement dimension table, we will complete the feature measurement and size evaluation for the CNC mill part. Once the coordinate system is established, we can proceed with the feature measurements. Now, let's proceed with the manual measurement of the features, following their distribution. The first dimension is the distance between two planes, with the associated features being reference plane B, plane 2, and plane 3. Next, use the probe to collect 4 points on each of the two planes, generating measurement commands for plane 2 and plane 3, which are then renamed PLN2 and PLN3. The second dimension is the distance between two planes, with the associated features being reference plane B and plane 4. Since reference plane B has already been established, next, use the probe to collect 4 points on plane 4, generating a measurement command and renaming it as PLN4. The third dimension is the distance between two planes, with the associated features being plane 5 and plane 6. Next, use the probe to collect 4 points on each of the two planes, generating 2 measurement commands, which are renamed PLN5 and PLN6. The fourth dimension is the distance between two planes, with the associated features being plane 7 and plane 8. Similarly, use the probe to collect 4 points on each of the two planes, generating 2 measurement commands, which are renamed PLN7 and PLN8. The fifth dimension is the distance between two planes, with the associated features being plane 5 and plane 9. Since plane 5 has already been established, next, use the probe to collect 4 points on plane 9, generating a measurement command, which is renamed PLN9. The sixth dimension is parallelism, with the associated features being plane 2 and plane 3. The measurements for these have already been completed, so simply select them during evaluation. The seventh dimension is the diameter, with the associated feature being hole 1. Next, use the probe to collect 12 points on hole 1 with 3 layers, 4 points per layer, generating a cylindrical measurement command, which is renamed CYL1. The 8th dimension is the diameter, with the associated feature being cylinder 2. Next, use the probe to collect 12 points on cylinder 2, with 3 layers, 4 points per layer. Before measuring, raise the probe to a safe position and change the probe angle to A90 and B90, generating a cylindrical measurement command, which is renamed CYL2. The 9th dimension is the diameter, with the associated feature being optical reference hole 3. Next, use the probe to collect 12 points on hole 3, with 3 layers, 4 points per layer, generating a cylindrical measurement command, which is renamed CYL3. The 10th dimension is parallelism, with the associated features being plane 10 and reference plane A. Since reference plane A has already been established, next, use the probe to collect 4 points on plane 10, generating a measurement command, which is renamed PLN10. The 11th dimension is the distance between 2 planes, with the associated features being plane 10 and plane 11. Since plane 10 has already been established, next, use the probe to collect 4 points on plane 11, generating a measurement command, which is renamed PLN11. The 12th dimension is the distance between 2 planes, with the associated features being plane 11 and reference plane A. Since these measurements have already been completed, simply select them during evaluation. During manual feature measurement, attention should be paid to avoid burrs and chamfers on edge positions. For features with limited clearance, parameters such as approach and retract distances need to be adjusted. Now, let's take a look at the manual measurement point distribution for elements. The minimum number of measurement points for manual measurements is shown in the table below. For measuring a point, only 1 measurement point is required. For measuring a line, at least 2 measurement points are needed. For measuring a plane or a circle, at least 3 measurement points are required. For measuring a circular groove, at least 6 points must be taken on the groove, usually 2 points on each side of the groove, and 1 point on the arc. For measuring a square groove, at least 5 points must be taken, 2 points on the long sides of the groove, and the other points distributed on the remaining 3 sides. For measuring a cylinder, at least 6 points must be collected on the surface of the cylinder. The first 3 points must lie in a plane perpendicular to the main axis. For measuring a cone, at least 6 points are required, and these points must be evenly distributed on the surface of the cone. The first 3 points must lie in a plane perpendicular to the main axis. For measuring a sphere, at least 4 points must be collected on the surface. These points should not lie on the same circle. 1 point should be at the pole of the sphere, and the remaining 3 points can be on the same circle. For measuring a ring, at least 7 points are required. The first 3 points should be taken on the circumference of the center line of the ring, on the same horizontal plane. These measurement points should represent the direction of the ring, and the vector of the hypothetical circle generated by these 3 points should roughly align with the ring's direction. When measuring, the more points are taken and the more reasonably distributed they are, the more accurate the measurement result will be. Therefore, in practice, the number of points taken is usually more than the minimum specified in the table. For example, for a cylinder, at least 3 layers should be measured, with at least 4 points per layer. Through this lesson, we have successfully mastered the manual measurement method for typical features on the machine demo part, and carried out effective dimension evaluation based on the measurement results. During the measurement process, we not only consolidated our previous knowledge of coordinate system establishment, but also honed our precision inspection skills. At the same time, we have gained a deep understanding of the importance of patience, attention to detail, and focus in precision inspection work. I hope everyone continues to maintain this learning attitude and continuously improves their professional skills. Finally, please reflect on this lesson and complete the following exercises to consolidate the knowledge you learned today and deepen your understanding. This lesson ends here. See you in the next lesson.